this computer. So first off, I need to make very clear that this lecture is this is gonna be resembling more of a traditional lecture. But I don't do, and this is just in case like we choose later in the semester, oh, the flip lectures aren't working. You understand what's going on. I don't do PowerPoints. When I lecture, I do live coding. So in other words, I'll be writing code, possibly coming up with examples as I'm writing them. But I don't do PowerPoint slides because I find that a waste of time and not very productive for computer science. We are not going to be doing Runestone today. Today is just me lecturing about for loops and that's the other thing I want to talk about. For loops are things that are going to be covered both this week and both today and next week. They are complex enough that I feel like you should definitely get exposure to them multiple times, each time as though they were the first time. Yes, I will go ahead and take attendance. Another question: are all the assignments on the book need to be scored? They need to be scored on my end. Or rather, I need to run the auto grader, which is what I'm going to be doing after class, as well as other. Yeah. So we're going to be talking about for loops, how they work today, and some of the basic things we can do with them today. Check-in has started for attendance, or it should start in just a bit because this is slow as molasses. When will the grades appear in Canvas? When I figure out a good, clean way to view them, but you should be able to check your grades in Runestone for how they're doing. Okay, I will try to get the grades some grades in Canvas this weekend, though. Your assignment grades will appear in Canvas. Your lab grades should be in Canvas just because that's where they are, but everything Runestone will pop up in Runestone, and I just have to find a clean way to export it. So, all right. Share screen. So today, because I think that just simply for issues of cleanliness and the fact that it works best, is that idle is a bit jagged when I drag it. I'm going to be working in, let's see, I'm going to be working in bars. Can you not see anything?
Nope.
But you can't see my desktop?
Oh, wait,
I just see File Explorer.
Very good. Oh, no, it was the way it looked on my end, not your end. So give me a second. So for loops.py, save file type as Python. So I'm here going to be using Visual Studio Code. That really shouldn't be too much of an issue. It's going to look pretty much the same. So we learned about for loop and what it kind of looks like. So for blank in range, and then we put in some number, let's say 10, colon. And then whatever we put indented inside of the for loop is going to look like this. Sorry, is going to act 10 times. So if I say print hello, and now if I go to run it, Python file. So the output appears down here. Conda, don't know why it's trying to use Anaconda, but anyway, there we go. We've got 10 instances of hello. See what happens if I run without debugging. Yeah, that works so much better. And so this for loop runs basically whatever we put in here some number of times. Now, as I've mentioned, and if I put in multiple commands, such as this, print hello, print world, each of those commands gets run once each time for each time the loop executes. Run with that. Oh, it's control. There we go. Hello world, hello world, hello world. So 20 lines total. Each of these things appear 10 times. So what makes a for loop, what makes a for loop powerful though is that we can kind of do quite a bit more with it actually. We can, this means basically I don't care about any changes from loop to loop, but often we do care about things changing from one loop to another. So for I in range 10, right? Let's go back to our previous example of hello. And that prints out hello 10 times. Now let's change hello to the variable I. And let's see what we print out here. Rather, yep, I'll just print it out first and then I will modify it. It prints out the following numbers: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So for I in range 10, print I. You can, so I was about to go, you can place you can replace the underscore. You use the underscore when you don't care about putting a variable here, but you can put any variable you want. You could put I, you could put J, you could put K. Mind you, if I put I, J, or K there, right, it's already warning me that's not going to work, but it's going to tell me I isn't defined, right? Creates a new variable to use inside the for loop named K. So, but it doesn't have to be a single letter. We can do for num in range, print num. And it's going to print out, since we said 10, 0 through 9. If we said 10, why is it doing 0 through 9? Why isn't it like printing out 10? What in the world is going on here? Let's go back to I, because that's a standard value that we'll be using a lot for this. Okay. So now let's go ahead and print out, let's go ahead and make this a bit more of a statement. I's value, or rather the value of I is, and now I'm going to do plus I. Now question, I just made a mistake here. What is my mistake? Anyone?
You did the plus sign. It should be a comma.
Right. So you skipped ahead just slightly, which is that, but it is the correct answer. Which is that basically I'm here, I is, as you can see down here, a number, right? We're printing out these numbers. And so I'm saying the value of this number is plus the number, but I'm adding, this is a string over here, and this is an int. Those don't mix together, so the way you combine those is you say str, so I need to turn this into a string. Or I could use comma instead of plus. There's a couple ways of doing that. So the value of I is 0. So the first time we execute this loop, the value of I is 0. The second time we execute this loop, the value of I is 1. The third time we go through this loop, the value of I is 2. Then 3, then 4, then 5, all the way up to 9. For a grand total of 10 times, right? There are 10 different values from 0 to 9, right? There's 10 different values there. There's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I know that seems a bit off. Computer scientists are weird. We start counting at 0. And pretty much that is the way that will work out. So this is a useful thing though, because we do have some capabilities here that we'll see. But this range statement is actually short for another, is actually a shortened, simplified form of the full range statement. Range 10 is actually short for range 0 to 10. You can specify what range of numbers we'd like to go over. So run without terminals, and you'll see that this runs the exact same thing. I is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So when we have range 10, that's short for a range of 0 through 10. For those of you who are more comfortable with the mathematical symbology, when we do range, pretty much when we do anything in Python and in Java and in pretty much every single other programming language, except for you, MATLAB, I'm looking at you, that when we look at ranges, it is basically written like this. It is inclusive of the first number, but exclusive of the second. In other words, it is the numbers 0 up to but not including 10. Make sense? The numbers 0 up to but not including 10. There's 10 different numbers there. All right? If this would be, if I put this in, what are the values? What does it go up to but not include? Yep, it goes 0 to 14, does not include the 15, right? Now, you might be wondering, why is this? And the answer is it actually makes some of the math pretty easy, because we can do cool things like this. 10 to 15. So if you haven't guessed, so by doing that, you should be able to make a guess as to what this does, which is that this is beginning to end. So it's going to be from 10 up to, but not including 15. 1, 2, 3, 4, 5. So that's 5 numbers, 10, 11, 12, 13, 14. And what's really nice about this format is that we can figure out, if you've got some number here and some number here, it's pretty easy to figure out what our numbers are. Specifically, we can, or rather, how many numbers are going to be printed out. Specifically, all we have to do is take the ending number and subtract the beginning number from it, and we'll get the total number of numbers, or the total number of times this will run. Right? 15 minus 10, there were 5 different numbers. So for instance, if I'm running 4 to 8, we can see that there are going to be 4 separate values, and we can figure that out just by doing 8 minus 4. Right? This goes from 4 up to but not including 8. Okay. But professor, what is the use of having these changing values? Well, I'm going to go ahead and draw something that you may see in some future videos, but I really like to do with our turtles, which is drawing some. So I'm going to start by showing you how to draw a spiral with a turtle. So because I'm not working in idle, I need to put in a statement at the end. This is only because I'm not working in idle or a textbook or the textbook. Turtle.done. And that will, so over here, comment this out, so it's not going to be red anymore. So it is the professor explains it basically, and then he jumps to something, and now I'm totally lost. But bear with me. I will explain it. Okay? So let's go ahead and draw a square. Basic square. 4 blank in range, right? Squares have 4 sides, right? Well, sorry, first we need a turtle. So let's go ahead and make Bob. It's equal to turtle.turtle. Okay. And then what we're going to do with Bob is we're going to tell Bob, we need you to move forward. We need you to move forward 100 pixels, please. And then we need you to turn right 90 degrees. And we want you to do that a grand total of 4 times. Now, if I didn't have the turtle.done, by the way, this is what happens. Just FYI. It's not wrong, but this is what happens. And we're done. Right? It just simply, turtle.done basically says, finish the turtle, but wait for the, basically it tells it, the turtle's done now. Wait for the user to tell you what to do before you end the program, please. And so now, we're done running. So, we've done that. So now suppose I change, so here's what I'm gonna do, and this is gonna look pretty cool. In range, so first off, let's go ahead and change this to 16. 16 ain't gonna do too much here. And I just changed it to I, and in fact, it's not gonna really do too much. All he's doing is drawing over his same line over and over and over again. Specifically, you know, done this a couple times. But this is something I find really cool. We can use the variable that we've made. Turtle.done is kind of like that. It's just easier to do, in my opinion, than like trying to remember windows and stuff and screens. Plus I. This isn't going to do too much. But let's see what happens when we do this. It might be a bit hard to see on your end, but the square is certainly getting thicker. What happened there? Well, what we're doing is that we are telling this turtle, we're telling the bob to move forward 100 pixels plus I pixels. 100 plus I pixels. Now, remember what happens here. I is a variable that changes each time we go through the loop. So, over to a whiteboard. You know, I purchased, oh, you have to install it? Interesting. It doesn't have to install it on my, didn't have to install it on my laptop, but okay. Hey, I remembered though that this has a built-in pen, so that's cool. All right. So here's Bob. First time we tell it to move, it's going to move forward 100 pixels, right? It's going to move forward 100 pixels plus I. Now, the very first time we run this loop, I is going to be equal to 0, right? So it's going to. So how much is he going to move forward? Anyone want to take one? Right, 100. Right. The math is easy here. 100 plus 0 is 100. So he moves forward 100 pixel. Then he turns right. So he's now facing this way, going down. Now we tell I is equal to 1 on our because we just did our first command. Right? We did our loop. When every time we go through this loop, I will increase. So now 1. So now he's going to move down how much? How many pixels? 101. Right. So, and then it gets down, finishes. So we went through our loop our second time, and we automatically increase our value to 2 now. Then he does 102 pixels, then 103 pixels, and then 104, not to scale. In fact, let's probably buff the size up just a bit to make it easier to see without making it horrendously horrifying to anybody. Okay. Let's go ahead and do some multiplication. I times 10. So first time, he's going to move 100 pixels. Then he's going to move 110. Then 120. Then 130. Then 140. Anyone completely and utterly lost yet? Remember, if you're lost, you can privately message me so that you don't have to worry about like feel like you don't have to be afraid, in other words. Because students can be very how would you go from outwards to inwards? Oof. Maybe subtracting. Let's see what happens if we subtract. go ahead and see what happens if we subtract and do, when you type the code in Indie, in idle, the 100 and the, yeah, the colors for these, the colors all depend on how your syntax is going to be highlighted by your specific IDE. All right, so somebody said that they were lost on this part over here, the for I in range. Right now it's commented out, so it's not doing anything. But when we did have it commented in, basically we were saying that I's values were going to be between 4 and 8. By default right now, when we're doing this, we are saying that this is running from the values 0 up to, but not including 16. And then turtle.done basically says not to close the turtle screen. You don't have to worry if you're using Runestone. All right, and what does the times 10 do again? Well, it's a bit hard to see it when we're dealing with, when we're just adding, so the reason we're multiplying I by 10 is because if we're just adding 1 pixel to run this, right? So we move 100 pixels, then we move 101, 102, 103, 104, 105, 106. It doesn't create too much of a gap between our lines, right? It's a bit hard to see. So what I'm doing is that I'm rather than adding 1 each time, or adding I each time, I'm adding 10 times I value, so that it's 10, so that we're adding 0, 10, 20, 30, 40, 50, 60, 70, 80 to 100. So now that's easier to see. So so for loops are really, really useful like that. I'm not sure. It really depends on what your code is. I mean, it's not really going to, it's only going to have the illusion of getting thicker if they're really close together. Don't worry, Nathan. Welcome to 1051, where attendance is made up and the points don't matter. So the so that is just kind of one of the big uses of the for loop here. We can do some really cool stuff with this. We can make it go a bit further, but we also have but that's not all we can do with for loops, right? This is just simply for I in range. And what I'm showing you here is going to be coming up a lot in chapter 7, and we haven't even hit and we're just now touching 5 and 6. So, but let's go ahead about for loops and sequences. .py, and let's see if it identifies it in Python. There we go. Cool. Okay. So first off, we've been talking about a lot of different data types. We've talked about our ints, we've talked about our floats, and we mentioned strings a bit. Strings are a type of thing, are part of a larger type of data called sequences, which are basically collections of things. So, right, a string is a collection of letters. And also so are lists. I'll be using strings for this example, but what's wonderful about Python is that it all works on lists as well. So let's go ahead and take a look at this use of the for loop. For I, so now let's go ahead and see word is equal to hello. For letter in word. So not for letter in range or anything. I'm saying for letter in word, print letter. So any guesses as to what this is going to do?
Um, Print out each character in the word hello.
Yes. So one of Python's big things is that it should be completely unsurprising how the basics work. So for letter in the word, print out the letter, right? These loops are sometimes called for each loops. So what we're doing is we're going to go through and print out every single letter in this. Just by saying for letter in for thing in sequence, you can go through each thing in the sequence one by one, which is really cool. Hello. Hello. So it is really nice to do that. Another thing we can do to, we can call this whatever we want for thing in Word. And now we will print it out. There we go. Same thing. Not sure why it was saying, hey, about something about a host, but hey. So it prints out every single letter in the word. There are also other things that, so this works also for what you'll find are called lists. And I'm going to expose you to them right now. Not really going to talk about too much more how to use them, but they're really awesome. So I'm going to go ahead and say list of words. Or actually, I'm going to say, actually, I'll show you a list of nums because that's easier types. List of nums. Why does thing work as same as letter? So let's go ahead before we move on. Why does thing work same as letter? Right, because because to be honest, yeah, it's just a variable name. The computer does not know what a letter is. It really doesn't. In fact, from its perspective, there are no such things as letters. They are just glyphs. They have no meaning to it. All it knows is that some things together are, yeah, so you could put I there, but honestly, I is typically used for index or integer. So I is actually, it's not wrong, it's just not the most correct choice for a variable, right? But I implies like a number. So often you might see something like for C in Word, or for like, that's short for character. But the reason is that whatever, you can put any variable you want there, and it's going to iterate through. Right? It's just simply the label for each individual that you're going to use as you go through each item. So let's go ahead and check out another sequence we have. There's really only two sequence types we use. There's another one called tuples, but we barely even touch on that. This is a list. Lists are pretty awesome. They are very simple to do. They are just saying, basically they look like something in between a bunch of brackets, or if you are dealing with, or if you're thinking more mathematical, it looks like it might look like a single dimensional vector. So here's a list of numbers. 1, 2, 3, 4, 5. That is my list of numbers. For thing in list of nums, print thing. So first thing we did is that we printed out every letter in the word, Hello, and then 1, 2, 3, 4, 5. Is each letter that prints out a string? Oh, excellent question, Aaron. So Aaron asked, is each letter that prints out a string type, or is it a character? And the answer is it's a string, because there are no characters in Python. Not really, no. There is just, that was needlessly, how to say, characters are just strings of size 1, essentially. There is no, since there are no primitives, there's no need for characters. Sorry, so everything, all text is strings. And if that made no sense to you, that's because you're not coming from a programming language. Yep, so that's why, yep, and that's exactly why it doesn't matter if you use double quotes or single quotes for strings. And for the context of other, for everyone else, other programming languages like Java and C, there are primitive data types called characters, which are noted by having a single quote mark in the beginning and end of that single character. And then you have strings, and then you learn strings and you promptly never use characters unless you're dealing with a string and going through it letter by letter. But Python doesn't care because Python is meant to be easy and get out of your way so you can get to important things like solving a problem. So when it prints out, excellent question. So when it prints out entries of the list of nums, will those be int types or string types? So let's go ahead and print, let's see, it's type. I think it is there is an instance of. I'm trying to remember multiple languages. There we go. According to survey says, integer. Excellent question, right? These are ints. I'm going to go ahead and show you though, right? So also you can, what I just did here is, it makes me a horrible person. Yes. Ollie asked, you can mix integers and strings inside a list? Yes, and I just did it, and that makes me a horrible person. So, because you really shouldn't do that, because it can be, programming is so much easier when you assume that everything inside the list is the same type. Okay, so notice over here you've got int, string. Okay, now you might be wondering why I'm doing this over here, because I'm going to bring it back to turtles, because there's something really awesome I like doing with turtles over here, which is, let's go ahead and go back to our spiral example. And how come it didn't print the string as a line like it did for the first for loop? What do you mean like a line?
Like, you know how in hello it first printed out HELLO? Why did it do for 3? It just printed out 3 in one line.
Oh, excellent question. So, because the way this works, is for thing in sequence. So in the word, that's each individual letter. In a list, that's each item in the list. So 1 is an item, 2 is an item, 3 is an item, 4 is an item, 5 is an item, the word 3 is an item. Does that make sense? This is an item in the list, so it's going to go through them. So now I'm going to show you in a kind of native way that, or a non-horrifying way, that basically the students have no problem dealing with for loops. It's when we start to do things like nest for loops that things become confusing. Fortunately, in Python, it's not really easy to, it's not really necessary to write, make work for loops, ones that just are nested for the purpose of just being a teaching example. The teaching examples are actually practical. So let's go ahead and write color spiral. All right, and let's go ahead and review some turtle commands. Okay, so first, import turtle. Okay, and let's just do some turtle aesthetic commands. Turtle.done, right? And we are going to say Bob. Why Bob? Because Bob is 3 letters and Alice is 5. That is the only reason. Turtle.done. So the it's not turtle.done, turtle.turtle. Let's let's go ahead and now do Bob dot shape, I believe. Yep, shape is, let's go ahead and turn him into a turtle. Turtle shape. And Bob dot shape size. So this will stretch the width and the height. So I'm going to say 2, 2. And now I'm going to say, yeah, Bob dot pen, was it width? We don't really need that. Bob dot shape size. And let's just see what Bob does. Bob dot forward is 100. So we can see our turtle drawing. Are there other animals you can make this shape? Not really, that are built in. There are ways to, though, have a picture and load it up to be the turtle, or to have a picture and load that up and be the background. What we build up to in this class for turtles is that we use turtles to build a hurricane tracker. So you give it a bunch of data from AccuWeather, and it plots the path and the magnitude of a hurricane. And it sounds really intense and really hard, but actually it's one of our easiest assignments once you actually let, it's one of our easier assignments once you let yourself not get overwhelmed by all the work that's already been done for you. Right? Again, Python's meant to make things easy, not to make things horrifying. So Bob.forward is 100. Now let's go ahead and say Bob.color is equal to red. When I comment out, if you're using idle and you use turtle.done, then it's, if you're using idle, you don't need to use turtle.done. If you're using, depending on what IDE you use, you might not need turtle.done. But because I'm using Visual Studio Code, I need turtle.done. So let's go ahead and write a simple for loop to do our square. So for I, so let's go for blank in range 4. Everybody agrees that this is going to be, that this is code that makes Bob draw square. Bob.forward. I will get in. I was thinking about going into that, but yeah, you can do that for colors. I'll be touching on color in a bit, so don't worry about it though. Bob.forward. Bob. In fact, actually, now might be a great time to do color. So, actually, yeah, let's do this. So shape size. All that did is basically made Bob twice the width and twice the height that he currently is. Makes him look bigger, so he's easier to see. So there's our code for this. Now, here's the thing you can do with for loops. You can nest them. Bob that pen up. What does that do? That tells Bob to raise his pen. Bob dot pen down to put down his pen, and Bob dot forward to tell Bob to move forward 100 pixels. Suddenly it looks very, very scary and very, very complex, but I assure you it is not. It just looks weird because you haven't seen it before. But what all this is saying is do the following 4 times. Do all of this 4 times. You don't need to write out forward. FD FD is short for forward, just like RT is short for right. But yes, I should be consistent. So what this does, it says, do whatever's indented inside me 4 times. Do whatever's indented inside me 4 times, which is move forward 100, turn right 90 degrees, which, as you know, this is the code that we've used to draw a square a bunch of times. Then what we say to do is Bob takes his pen up, moves forward 100 pixels, then puts his pen down. Then he runs this again. So what we do is that this makes Bob draw 4 squares. So how many people did I lose? Surely I lost a bunch of you there. Okay. Excellent. Okay. Okay. So remember, what all a for loop says is, it says, so all a for loop says is that I want to do what's inside this. When we write a for loop like this, for blank in range 4, it says do whatever indented inside the for loop created at line 10 4 times. Okay, yeah, I'll move this guy forward 150. This is 100, and then we say to do this block of code. So each time this outer block of code runs, we draw a square, tell Bob to move his pen up, move forward, and put his pen down. And we do that 4 times. So there we go. There we go. It is now if I don't want to do some weird kind of drawing. Thank you for the suggestion, Cameron, by the way. So for loops can be nested, and they're basically you can say use this, and basically you could say, hey, repeat this thing multiple times, repeat the repetition. Yep, if this is inside this one, then it gets really weird, right? Remember, whatever you're indented in is the for loop that you're in. So if you run this, this is going to be really weird. So draw square, move forward, draw square, move forward, draw square. So that's a really cool thing we can do with this. Now, however, I did not say this. I said this was color spiral. So let's go ahead and talk about color for a second. So what is color? Anyway, we can. So what is color? Well, here's a good comic I think describes it. My evolution of color over time. Grade school to now. Color is 3 primary colors mixed together. A rainbow, each color is a wavelength. Unknowable, maybe what you see as blue, I see as blue, you see as. Grade school is like 3 primary-ish colors mixed together. RGB, red, yellow, blue, red, green, blue, cyan, magenta. Yeah. Something about opponent a model, or a mix of infinite wavelengths filtered through the fact that we have 3 different things. We have 3 different colors to see in our eyes. Abstract multidimensional gamut. Abstract into multidimensional gamut filtered through inconsistently implemented device color profiles. Oh yeah, yeah. So that's a pain. I'm sure many of you were wondering why in the world, like Apple, like a year or so ago, released a $5,000 monitor. And the answer is, if you don't know what you need a $5,000 monitor for, you don't need that $5,000 monitor. But one of the big reasons is that a lot of devices, it's hard to get colors accurate. So, and you know, essentially, just when you get the chance, when we're not all socially distanced, you know, just have a friend pull up one picture on their phone and pull up a picture on your phone, and just see if the colors are exactly the same. They're not, but hopefully somebody else's problem is the idea there. In terms of computers, though, we use the RGB model. We basically define color as reds, greens, and blue. Okay, let me go ahead and say bob.color. This will print out what the color is. And this will be probably what I don't want. It will probably say that it is, oh, print out red, red. Okay, that's unuseful. So let me just go to the Google machine for a second. Turtle Python API. Turtle graphics. Control F, color. Okay. That's not what I need. I need color over here. Yes, I know you cannot see what I am doing. Color mode. That's annoying. Do I have to really do it in, yeah, you could do color in parentheses, kinda. The issue is that the default way of doing color is that it uses a, here, I'll show you. If you try to, I think if I do like 10, 5, and 255 right here. Sorry, no. If I try doing that like that, will give me an error saying that it's a bad color sequence because it's expecting something between 0 and 1. So, oh, right. That's what it is. So let's see. Color mode. We'll just have to remember how to do this properly. Okay, that should fail, I think. Color mode is not defined. Turtle.color mode. There we go. Okay. So turtle.color mode, this basically puts it into the standard color model that most of us are, that if you've messed with color, you're familiar with, which is that basically color is made up of 3 different colors. The amount of red, the amount of green, and the amount of blue that you want. So for instance, by setting Bob's color to 0, and you just put it in parentheses like this. Actually, can I do it like this? Let's see. Yes, I can. Okay, cool. I don't have to put in a tuple. So you can put in, to change color, you can either put in a word for your color, or you can put in what's called, or you can put in the red value, the green value, and the blue value. So let's go ahead and see. So this is blue. So if I do all 0, that's going to be black. And then if I do 255, that is the maximum value you can have for a color. Why 255? Because that is the maximum value you can have for a byte. And all those is, I didn't even read the question. I knew somebody was going to ask. Why 255? Because color is defined by, because color in most programs, although it's changed nowadays, is defined by an 8-bit number, which means that it has a grand total of 2 to the 8 different values. 2 to the 8 is 256. So that you can have 256 different values for a single color. And remember, because we're doing computers, since 0 is a value, that goes up to but doesn't include 256. So 255 is the highest color. Did that answer your question? Oh, okay. So let's go ahead and see. This is blue plus green, or green plus blue. Yeah, 0 is black, and 255 is white. This is cyan. So green plus blue is this cyan color. 0 is basically no color, or possibly. It really depends on how you look at it. That is a philosophical question, because remember, actually, 0 would be a lot of color, right? 0 because all the color is being absorbed. All the red of the white light is being absorbed. All the blue light is being absorbed, and all the green light is being absorbed. But why does it only go up to 255? Because those numbers are, because that's just the max on the computer. Yeah, because because we're dealing with, because each color is made up of a byte, and a byte holds 2 to the 8th is made up of 2 to the 8 bits, which is and that 2 to the 8th is 256. 0 to 255 is 256 different values. That's okay. It's just I'm not an artist. I don't know the color models. Mine doesn't change colors. I'm not sure. Yeah, if you look at a color wheel online, it'll make more sense. Most of the time, you'll see something like a hash value with a number. I mean, it could be a philosophy class. All right, so we've got this color here. Let's go ahead and add maybe 100. Let's go ahead and add 150 red. So it's kind of a crimsonish color, crimsony color. So let's go ahead and start out with, so here's one thing that I like to do. Well, let's start out with a lot of blue. Okay, and here's what we're gonna do. I'm going to go ahead and now say, I'm gonna write a for loop here. For I in range, or let's see, for red in range 0 to 255, let's go ahead and draw something pretty interesting. Bob.forward. Let's move them forward 1 pixel. But before we do that, we're going to say bob.color is equal to the amount of red in this value with the blue, with 0 green and 255 blue. Going to go pretty slowly, but look what happens. He slowly changes color. Now it's a bit hard to see, unfortunately, but you can see that basically we are adding in more and more and more red as we go on. We could make the pen size thicker, but I'm not going to do that. I'm going to nest this.
Professor, you should make the pen size thicker so we can see the colors better.
Don't need to. Trust me. All right, so we move forward 255. So once we finish going, so essentially what we're going to do is we're going to say 100. We're going to draw 100 lines right next to each other. So what we're going to do is that he's going to move forward increase the amount of red and for a certain amount of blue. Now this outer loop controls the amount of blue and the inner loop controls the amount of red. And this is easier to see what's going to happen when we're done with it. But what we're going to do is say Bob, once we're done with this, we're going to say Bob dot pen up, Bob dot backward rather than forward. I'm not even going to bother making. Actually, I should probably make him turn. So Bob dot left, turn around 180 degrees. Nah, he's going to have to do it anyway. So Bob dot backward 100. Oh, sorry, he's going to move forward 255 steps, right? Because he's moving forward once 250 times. So I'm getting back to where he is. So that's where he started, and now we need to move him slightly down. So Bob dot right turn 90 degrees. Bob dot forward 1, because we're moving him down 1 pixel. And then Bob dot left turn 90 degrees to get him facing the same direction. So, oh yeah, and Bob dot speed is 0 because we want this to move a bit faster. 0 is like the max speed. So it's going to go pretty slowly, to be honest, but you'll see what happens here. Yeah, this is going to be a bit slow, unfortunately, so let's go ahead and speed this up. Yeah. So we are going to now show you I'm going to now show you the last part of the range statement. Range statements can have a third argument. By default, it is 1, and that is the amount that you go up, that is the interval. So by default, 255 means from 0 to 255 up by 1s. You know what? I think I got completely diverted by that. That is a great question, Cameron. I got totally distracted by turtles. But I get the same, but I'm getting the same, why am I mute? Why is my sound muted? Yeah, I'll probably do the pie in a separate, in videos instead, because honestly, this is way more fun, I think, for people. Yeah, plans never survive first contact with the enemy. Or as Patton said, I believe, plans are useless, but planning is essential. So here, rather than going up by, all right, so here, rather than going up by 1, we're going to go up by 10s for red. So the transition should be a bit quicker, and as a result, we'll also have Bob move forward 10. So this is just going to effectively speed it up. Let's see. Ah, ha, ha. I see what happened there. Guess what I forgot to do? Yep, pen down. I forgot to do pen down. Essentially, oh, yeah, this is gonna be a bit weird because it's jagged, but you can see that we're kind of creating a color gradient because the amount of blue that we're doing goes down a bit, but the amount of red that we're why is it jagged? It's because I'm going from up to 255 here. So I'm going to just go up to 250 and do 250 here. This will make it stop being jagged. The numbers didn't match up because I was going up by 10 for the sake of speed. I am very sorry that this does not work for colorblind folks so much. Amazing how one cutscene from one video game has changed how we communicate. Call of Duty. Press F to play. Press F to play pay respects. I've actually never played any Call of Duty games really, because I just haven't. It was never really my thing. So anyway, this draws us a gradient. It will take a while. But you can see what what we were doing over here is that we were drawing the amount of red and we were slowly subtracting out the amount of blue that we had. So that's what we can do really cool things with this turtle. Yeah, red is this variable. It's basically where we're increasing the amount of red. And then we were decreasing the amount of blue each line, although that wasn't necessarily apparent. Although I will make it more apparent now. Let's start from, nope, we wanted to go, sorry, forgot I was subtracting for a second. 0 to 250 minus 10, so. What did I forget? Invalid name. Okay, what crashed here?
Should be positive 10.
Yep. I was making a deliberate mistake. Obviously. That's my story and I'm sticking to it. What was the third argument for? We'll get into more detail, but right now we can see it getting more and more red and the blue starting to kind of fade out here. So I think in the last 20 minutes, so yeah, I think this is good for turtles. So I do actually want to touch on pi just a little bit, though. Thank you for the reminder. Because pi is very good at showing us how to do how to use the third pattern called an accumulator. So so what is the value of, what is the value for pi is what? 3.14, but what makes pi special in terms of what kind of number is it? What number class is it? It is an irrational number, right? You can't have an argument with it. No, that just means that you cannot, you cannot write pi as a fraction, essentially. Will this code be available on Canvas? I'm going to throw it on GitHub, so on the GitHub link. So, but pi is pretty cool. So basically, though, if you can't express it as fraction, it actually begs the question of how in the world did we figure out what the value of pi is in the first place? Like, we know for a number of digits, but how did we get 3.1415? Right? And so that brings us to approximating pi. Now, actually, so one of my favorite math classes was numerical analysis. It was possibly the easiest math course I took. Not because only because I was a computer scientist, because it was all about basically, there were other classes. I went to a school where there were a lot of engineers, and engineers would have to take differential equations and annoying stuff like that. But honestly, those are hard. Math is hard, right? What's easier is doing approximations, estimations that are way easier. So in other words, get your computer to do it for you, and any error in the estimation that your computer does, so any estimation that your algorithm has should be smaller than like whatever the computer can hold. So currently, let's see, we've got the world record length of pi is 31 trillion digits with the help of Google's cloud computing service. But honestly, we've done a lot of different ones, a lot of different equations. One of my personal favorite ones, which is one of these fractions over here. Shangxi. Two other approximations. 355 over 113. It's actually a really good approximation of pi. But otherwise, we have algorithms that help us calculate pi. So let's see. There's some awful ones here, but we have polygon inscribed like a circle. Nah. Yeah. Other classical formula. This one, Euler's, Ramanujan, all of them have different formulas. But honestly, there are different ones that we can do. Oh, this one's fun. This one is my personal favorite, the Gregory Leibniz series, which is that we can estimate pi that by doing this. Or specifically, we can estimate pi by adding 1 minus 1/3 plus 1/5 minus 1/7 plus another number, and so on and so forth. Let's see. Why can't Archimedes had his own approximation of pi. Yeah, but this one is a lot easier for us to kind of program over here, which is that essentially we can do it this way. So what we're going to use is a very common pattern called the accumulator pattern, which is essentially we are going to add numbers up. So for instance, summation is equal to 0, and it looks like this. Summation is equal to 0 for num in range 0 to 10. Summation summation is equal to summation plus the number. And this will add up all the numbers from 0 to 9. I said it would add up all the numbers from 0 to 9. What in the world just happened there? Summation. There we go, 45. So the idea here is that you take this number, you add, so you start at 0. You take 0, add 0 to it. Then you take 1 and add to summation. So we're at 1. Then you take 2 and add to summation. We're at 3. Then you take 3 and add to summation. We're at 6. Then you take 4 and add it. You're at 10. So we keep adding numbers on and on and on here. This pattern called the accumulator is used a whole lot for computing averages, for just adding things up. It's very useful. So let's take a look at this formula. we can totally add this up. And I don't think there's actually enough time in 10 minutes to explain the accumulator pattern in full detail. So the pi thing won't really work too well. But the idea here is that we can compute pi over 4 pretty easily, right? This computes pi by basically multiplying this by 4. If we divide 4 out of this, we get pi over 4. Pi over 4 is equal to 0. Start out there. And so what we need to do is that we need to add these series. And basically, the more numbers we add in this series, the more accurate pi is going to be. So miles is equal to 100. So we're going to for I in range trials. And now we have to figure out what changes each time for this loop? What changes each time in the number? Well, the denominator changes, 1, 3, 5, 7, and the sign changes. So let's go ahead and do sign is equal to 1, and then denominator. So sign we'll set to be positive by saying it's 1. Sign is equal to 1. Denominator is equal to, let's see, it starts out at 1. So 1 plus I, because you're going to get 0. And then the next thing, the denominator goes to 3, right? And then it goes to 5. Then it goes to 7. Then it goes to 9. So what do we? So what should we multiply I by in that case? Yep, 2i plus 1. So let's see there. We've got 4i in range trials, sign, denominator, and then what we're going to do is that we are going to basically add pi over 4 is equal to sign times 1 over the denominator. Sign is equal to what we currently have. And then what we have to do is we have to flip the sign for the next number. Sign is equal to sign times -1, which will flip it. So, and why doesn't it do anything? Because I forgot to print something out. So to figure out what pi is, it's a completely new keyboard, so the keys are completely in. It's going to take me a couple months to get used to everything. So print pi over 4. Do I not have to put a parentheses around it? Nope. Because remember, it is sign times 1 over denominator. So multiply this by 1 and then divide it. So it's going to be perfectly fine. Pi is pi over 4 times 4 to get the actual value for pi. So if we run this 100 times, we should get 3.1315929. It's actually pretty funny how close yet how off it is, right? And so if we do this 1,000 times, and my computer can handle it, 3.14059.265. So it's kind of like weird. What's cool, and the reason I also wanted to do this and end with this is just to emphasize something about modern computers. How many trials was that? That was 1,000,000 trials that it just spat out like that. Specifically, it adds up 3.14159. It's not that accurate. In fact, it mentions that it is conversions too slow to be of any practical interest. But that's okay. Speed is very very good. Now, this is what we call a linear time algorithm. It's going to run once for every trial. So if I do 10 times more trials, it should take me 10 times as long to give me something, right? When we were at 1,000,000, it paused a bit, right? Watch for the hiccup when we do 1,000,000. Run, hiccup, there, okay? So now we did 10 hiccups in a row, essentially. So this is about as large as is reasonable for this computer to do. So that is 10,000,000 runs. All right, what does the plus equals mean? Okay. Plus equals is a shorthand for this. I meant to avoid doing that, and then I just did. But what this does is that it means add this to that. This is the same as doing plus equals over there. If this part went whoosh over your head, that's perfectly fine. I just wanted to do this to kind of emphasize that this is insane. 10,000,000 math operations in less. Do plus plus and minus minus not work in Python? No, they do not. Plus plus and minus minus do not work in Python because plus plus and minus minus are bad. Yeah, plus plus and minus minus are bad. And here's why for our last lesson, for people who are coming from another programming language. If you're coming from something like Java, and I ask you, A is equal to 8, and B is equal to 5, and I ask you what is A plus A plus B plus plus, what's that number gonna be? Sorry, what are A, B, and C gonna be? Because A over here means increment A before doing the operation, so A becomes 9, and this says increment B after doing the operation, so B becomes 6. But why do it like this when you could split it up into multiple lines and make it easier to read? All right. I will not put the code on Canvas, but what I will do is I will put it on GitHub. So last thing to see that, so I will upload the code. Let's go ahead and go to Canvas for a quick second. So Canvas. Click here for GitHub. All the code is here, or all the code that ever was here, for this class at least. You are ITP, Intro to Python. Click here. There will be a folder for your semester shortly that you'll be able to click on, and you'll be able to see the code there. You can also peruse the code from previous semesters. All right, so don't worry if you missed the last bit about Pi, but this is the introduction into for loops. Hopefully, this should be more than enough than what you need to do the current assignment. So for the upcoming readings and lectures, I'm going to be going over more about turtles, sequences, and more about how these for loops work, although I did a pretty good job of going over it today. Once we learn for loops, we will work on let's see. Once we work on for loops, we'll go over if statements and then functions, and that's pretty much most of the building blocks you need. After that, we'll talk a lot about file reading, because file reading is where we will go through, is where basically this really branches out. Okay, class is dismissed. If you need to demo, you can stay behind. Could I do a tutorial of GitHub someday? I suppose, if I must.